You are listening to a planet, not its heartbeat, not a metaphor. What you're hearing right now are real radio waves, electromagnetic pulses captured by NASA spacecraft radiating from the largest world in our solar system. Jupiter does not just sit quietly in space, it broadcasts, it roars, it generates radiation bursts powerful enough to travel millions of miles through the vacuum, strong enough to be picked up on Earth with the right equipment. And we have only begun to understand what it's trying to tell us. This is the planet that holds more secrets than any other in our solar system. A world so massive that if you hollowed it out, you could fit every other planet inside it and still have room left over. A storm that has raged for at least 2 centuries, possibly longer, with no end in sight. Winds faster than anything that blows on Earth, lightning more powerful than any bolt that has ever crackled across our sky. And beneath all of that, beneath the clouds, beneath the storms, beneath even the reach of our most sophisticated instruments, something we still cannot explain. Something that is quietly rewriting everything we thought we knew about this planet. This is Jupiter, and this is the story of how, the more we look, the stranger it becomes. To understand why Jupiter matters, why it has commanded the attention of astronomers for 4 centuries, you first have to appreciate its sheer scale. Jupiter's diameter stretches more than 86,000 miles across. That's not a typo. Put another way, you could line up 11 Earths edge to edge across its face and still have space to spare. Its volume is so immense that 1,300 planets the size of Earth could fit inside it. And its mass? Jupiter accounts for more than 2/3 of all the planetary mass in our solar system combined. Every other planet, moon, asteroid, and comet, all of it together, still doesn't equal one Jupiter. And yet, for all its enormity, Jupiter is not a slow, lumbering giant. It spins faster than any other planet in the solar system. One Jovian day, one complete rotation, lasts less than 10 hours. 10 hours! For a planet that wide, that means the equator is moving at roughly 28,000 miles per hour just to complete a single rotation. That speed is not without consequence. It is in fact the engine driving nearly everything we see on Jupiter's surface. Those iconic stripes, the orange and white and amber that make Jupiter instantly recognizable, are not just decoration. They are the visible signatures of one of the most powerful atmospheric systems in the known solar system. Jupiter's atmosphere is organized into east-west flows, rivers of wind that encircle the entire planet at different latitudes, each moving in the opposite direction of its neighbor. Where cold, bright ammonia ice rises from below, it forms the lighter zones, pale gold and white, reflective and luminous. Where warmer gas descends, we see the deeper layers beneath, tinted with compounds like ammonium hydrosulfide that give off those rusty amber tones. These are the belts, and in between, the jet streams. Wind speeds here reach and exceed 400 miles per hour. For context, the most intense hurricane ever recorded on Earth peaked at 215 miles per hour. Jupiter's ordinary, everyday atmospheric winds nearly double that. And those winds are not localized to one storm, one region, one season. They wrap around the entire planet in bands thousands of miles wide, and they have been doing so for as long as we have been watching. What drives them? In part, it is Jupiter's rapid spin. The Coriolis effect on a planet that quickly is simply devastating in its power, fracturing the atmosphere into dozens of distinct jet streams. But there's another engine at work, one that makes Jupiter fundamentally different from a planet like Earth. Jupiter radiates more heat from its interior than it receives from the sun. Deep within the planet, still radiating the thermal energy left over from its violent formation billions of years ago, is a furnace that never went out. That internal heat drives convection, warm gas rising, cool gas sinking, which continuously fuels the atmospheric circulation above. Jupiter's storms are not powered by sunlight. They are powered by the planet itself. This is a world that generates its own weather from the inside out.
In the southern hemisphere of Jupiter, there is a storm. Not a hurricane, not a typhoon. Those words are too small, too terrestrial, too ordinary for what we are looking at. This is the Great Red Spot, an anticyclone, a colossal high-pressure vortex that has been churning in Jupiter's atmosphere since at least 1831, and possibly much longer. It is roughly 1.3 times the width of Earth. Its outer winds race at up to 268 miles per hour. It rises above the surrounding cloudscape like a blister on the atmosphere, topped by a dome of reddish haze that sets it apart from everything around it. For a long time, people believed this storm had been watched continuously since the 17th century, since the Italian astronomer Giovanni Cassini observed a large atmospheric oval between 1665 and 1713. The romantic image of a 400-year storm became part of Jupiter's mythology. But in 2024, a careful analysis of historical observational records suggested a more complicated truth. The permanent spot that Cassini documented was in all likelihood a different atmospheric feature, one that had since disappeared. The modern Great Red Spot was most probably first observed in 1831. That still makes it nearly 200 years old. The storm was already raging when Charles Darwin was formulating his theory of evolution. It has outlasted empires, revolutions, the industrial age, the space age, and the digital age. It shows no signs of stopping. What sustains it? The same jet streams that organize Jupiter's atmospheric bands also maintain the Great Red Spot. The most compelling model links the storm's origin to an instability in the shear flow between neighboring jet streams. When two adjacent rivers of wind blowing in opposite directions develop turbulent instabilities, the result can be a vortex that, once large enough and stable enough, becomes self-sustaining. The surrounding jets essentially act as walls, preventing the storm from drifting freely and protecting it from being torn apart. The color itself remains partly mysterious. The reddish-orange hue may come from complex organic molecules or phosphorus-bearing compounds dredged up from the deeper layers of the atmosphere. At high altitude, sunlight can chemically alter these compounds, deepening their color. The exact recipe is still being debated. What is not debated is that the Great Red Spot is shrinking. When it was first reliably measured in the 19th century, the storm was approximately 25,000 miles wide, large enough to fit 3 Earths across it. By the 1970s and 80s, it had contracted to roughly 15,000 miles. Today, it is approximately 10,000 miles across. The shrinkage has been gradual but relentless, and no one fully understands why. Some researchers have suggested it may be absorbing smaller storms, cannibalizing them to maintain its energy. Others argue that changes in the surrounding jet streams are starving it. In recent years, the storm has also been observed to take on a more circular shape, whereas it was once distinctly oval and elongated. Whatever is happening, the greatest storm in the solar system appears to be slowly, very slowly, fading. And here is where things get profoundly interesting. Because one of the most startling discoveries made by NASA's Juno spacecraft, which has been making close polar flybys of Jupiter since 2016, concerns not the breadth of the Great Red Spot, but its depth. Using microwave instruments and gravitational measurements during close flybys directly over the storm, scientists were able to probe beneath the cloud tops. The result was surprising. The Great Red Spot, for all its terrifying width, is remarkably shallow. It appears to extend only about 125 to 300 miles beneath the visible cloud layer. At pressures of roughly 100 times Earth's atmospheric pressure, the storm structure simply stops.
Compare that to Jupiter's major atmospheric jet streams, which Juno discovered extend downward for approximately 2,000 miles. The Great Red Spot, the largest storm in the solar system, reaches only 1/10 as deep as the ordinary winds flowing around it. The most famous feature on Jupiter's face is, in geological terms, barely more than a scratch on the surface, which raises an immediate and unsettling question. If the Great Red Spot barely scratches the surface of Jupiter's deeper dynamics, what is happening in those next 2,000 miles down and below that? That question turns out to be the most important one in all of modern planetary science. Because when scientists tried to answer it, they discovered that Jupiter's interior is nothing like anyone expected.
The Great Red Spot commands our attention. But to understand Jupiter, you have to look past it, to the entire canvas of storms and vortices that fill the atmosphere from equator to pole. At nearly every latitude, the boundaries between the jet streams are turbulent and chaotic, where two rivers of air moving in opposite directions grind past each other. The wind shear produces elaborate curling, wave-like structures, Kelvin-Helmholtz waves, that roll along the cloud tops like the crests on a disturbed pool of water. Dark, elongated structures called barges drift through the belts. Bright popcorn-like eruptions mark powerful convective thunderstorms surging upward through the cloud layers. Elongated white oval anticyclones circle the planet at mid-southern latitudes like a string of pearls. 3 of these white ovals, each having existed for decades, merged in the year 2000. The result was a storm called Oval BA, quickly nicknamed Red Spot Jr. by astronomers. Within a few years, Oval BA turned distinctly red, likely for the same reasons the Great Red Spot is colored, and reached roughly half the Great Red Spot's size. It orbited Jupiter in the same latitude band as its largest sibling, and for a period, the two storms interacted, approaching and then veering away from each other in a complex gravitational dance. Jupiter's atmosphere, in other words, is not just home to one great storm. It is a breeding ground, a storm nursery, a place where vortices are born, grow, merge, and sometimes persist for decades without a solid surface to slow them down or dissipate their energy. But it is when Juno flew over the poles that everything changed. Visual. View from directly above Jupiter's North Pole, the polar cyclone system in stunning detail. Geometric symmetry emerges. Prior to Juno, our images of Jupiter were almost always taken from near the planet's equatorial plane. The poles were poorly understood, distant, foreshortened, difficult to observe. Juno's highly elliptical polar orbit changed everything, and what it found defied expectation. At Jupiter's North Pole, a single central cyclone surrounded by 8 more cyclones, evenly spaced, arranged in a near-perfect octagonal pattern. Each of these storms spans roughly 1,500 to 1,800 miles across. They spin counterclockwise, their spiral arms nearly touching, and yet, in a discovery that still puzzles theorists, they do not merge. They do not crowd each other out. They hold their positions with an almost uncanny geometric stability, as though some hidden rule of planetary physics is keeping them in formation. At Jupiter's South Pole, a different arrangement, but equally remarkable. 5 cyclones surrounding a central one, and later a 6th joining the ring to form a hexagonal pattern. These polar clusters have remained stable for every year of Juno's observations. Nothing like this had been seen on any other planet. Saturn has a single hexagonal jet stream at its north pole, a famous and mysterious structure. But Jupiter has entire polygons of cyclones, self-organizing into geometric forms that defy easy explanation. The leading theoretical explanation involves a balance between the tendency of cyclones to drift poleward, because in a rotating planetary atmosphere, cyclones move toward the pole on a spinning planet, and the repulsive effect between neighboring vortices that prevents them from merging.
When these two forces reach equilibrium, the cyclones settle into evenly spaced, stable configurations, and the mathematics of that equilibrium happens to favor polygonal arrangements. But the details remain unresolved. This is one of the frontiers of planetary atmospheric physics. And beneath all of this meteorological spectacle, there are the lightning storms. Lightning on Jupiter was first observed in 1979 when the Voyager 1 spacecraft flew past and its cameras caught brief flashes of light on the planet's night side. The discovery was electrifying in every sense. Scientists had long suspected that if Jupiter had thunderstorms of sufficient vertical extent, if water could exist in all three phases, ice, liquid, and vapor, just as it does inside Earth's most powerful cumulonimbus clouds, then the charge separation mechanism that generates lightning on Earth would operate there too. They were right, and then some. Some lightning bolts on Jupiter release energy several orders of magnitude greater than the most powerful lightning ever recorded on Earth. Juno detected thousands of lightning flashes, and its radio instruments captured their electromagnetic signatures, whistlers, the same crackling radio waves that terrestrial lightning produces as it flew over the cloud tops. Jupiter's deep atmosphere thunderstorms are enormous, towering convective structures driven by the planet's internal heat, rising 30 miles or more above the surrounding cloud layers. But the Juno mission brought an extraordinary new discovery, a type of lightning that no one had anticipated. High in Jupiter's upper atmosphere, in regions far too cold for ordinary liquid water to exist, Juno's instruments detected electrical discharges. This was paradoxical. Lightning, as we understood it, requires liquid water, specifically the collisions between rising ice crystals and falling hailstones in the presence of supercooled liquid water droplets that strip electric charges from one another. Without liquid water, how could you have lightning? The answer came from an unexpected quarter: ammonia. Jupiter's atmosphere is rich in ammonia gas. When powerful convective storms hurl icy hailstones upward, 15 miles or more above the usual cloud decks, they enter regions where ammonia is abundant. Ammonia acts as a powerful antifreeze. It mixes with the ice on the surface of the hailstones, forming a slurry of ammonia water slush, a substance that planetary scientists have taken to calling mushballs. In these strange alien thunderclouds, collisions between rising ice crystals and descending ammonia-soaked hailstones generate static electricity in the same basic way that ordinary terrestrial hail generates it. The result? Lightning crackles through Jupiter's upper atmosphere, far higher in the cloud structure than the laws of terrestrial meteorology would ever have predicted. These shallow lightning bolts flash through ammonia clouds, briefly illuminating towering storm structures with eerie light, lasting just milliseconds, yet glowing nearly as brightly as ordinary lightning strikes. And there was a bonus discovery. The mushballs solved a mystery that had puzzled scientists for years. Measurements of Jupiter's atmosphere had consistently shown lower ammonia concentrations in the upper layers than the models predicted. Where was all the ammonia going? The answer turned out to be right there in the lightning storms. The mushball hailstones were laden with ammonia. As they fell from the upper atmosphere back down into the deeper layers, they carried the ammonia with them, removing it from the upper atmosphere and depositing it far below where our instruments could easily detect it. Jupiter was hiding its own chemistry inside its storms.
If you could see Jupiter's magnetic field, the planet would appear to be the most dramatic object in the sky. Its magnetosphere, the region of space dominated by Jupiter's magnetic influence, extends roughly 4 million miles toward the Sun and stretches an almost unimaginable 600 million miles in the opposite direction, forming a vast magnetotail that the inner solar system's planets actually pass through. Jupiter's magnetic field is estimated to be somewhere between 16 and 54 times stronger than Earth's, and it is not generated the way Earth's field is generated. Earth's magnetism arises from the churning of liquid iron in its outer core, a rotating metallic conductor producing an enormous electromagnetic dynamo. Jupiter has no iron core in that sense. Its magnetic field is generated by something stranger: metallic hydrogen. Under the extraordinary pressures that exist deep inside Jupiter, millions of times the pressure at Earth's surface, hydrogen, the simplest element in the universe, undergoes a phase transition. Its electrons are stripped free from their nuclei, and the hydrogen behaves not like a gas or even a liquid, but like a metal. It conducts electricity. And when an electrically conducting fluid rotates inside a planet, it generates a magnetic field. Jupiter is, in essence, a magnetic dynamo the size of a small star. The most detailed map of Jupiter's magnetic field to date is called the JRM-33 model, built from dozens of Juno polar flybys. It reveals a field of extraordinary complexity, not the smooth, symmetrical dipole that a simple model would predict, but a landscape of magnetic hills and valleys, anomalies and irregularities. The outer boundary of the main magnetic dynamo appears to sit at roughly 0.81 times the planet's radius, meaning the metallic hydrogen layer begins about 19% of the way down from the outer cloud tops. That translates to a depth of approximately 13,000 miles below the visible atmosphere. But one feature in the magnetic map stands out immediately, even to the untrained eye. Visual: Jupiter's magnetic field map, the great blue spot highlighted near the equator, a region of unusual field intensity glowing in false color. Near Jupiter's equator, there is a powerful anomaly, an intense concentration of outward-pointing magnetic flux with no clear counterpart anywhere else on the planet. Scientists call it the Great Blue Spot, a counterpart in a sense to the Great Red Spot in the atmosphere above. The Great Blue Spot marks a region where the magnetic field emerging from the dynamo below is unusually concentrated and unusually powerful. And what makes it even more extraordinary is what happened when researchers compared the Great Blue Spot's position in one Juno magnetic map against its position in the next. It had moved. Not by much, not by a dramatic leap across the globe, but by a small, measurable, reproducible amount. The Great Blue Spot is drifting, and this phenomenon, the slow change in a planet's magnetic field over time, is called secular variation. On Earth, secular variation is well known. Our magnetic poles wander slowly over decades and centuries, driven by the complex fluid motions in our outer core. Jupiter's secular variation tells the same kind of story, but what it reveals about Jupiter's interior is stunning. The most consistent explanation for the drift of the Great Blue Spot is that Jupiter's atmospheric jet streams, those powerful east-west winds, extend far deeper than the cloud tops, down to approximately 2,000 miles below the visible atmosphere. At that depth, hydrogen has become sufficiently electrically conductive that the moving fluid can physically drag magnetic field lines with it as it flows, altering the distribution of the magnetic field at the surface over time. The winds observed in the cloud tops are the visible tip of a structure that reaches all the way down to the boundary of the electrically conducting interior. And the motion of that deep-seated fluid is leaving its fingerprint on the magnetic field. 2,000 miles. That number keeps appearing. The deep jet streams reach 2,000 miles. The magnetic variation is caused by flows at 2,000 miles depth, and gravitational measurements suggest a boundary layer in the interior, a transition zone between the dynamically active outer atmosphere and the deeper, more quiescent interior, sits at roughly the same depth. Something important is happening 2,000 miles beneath Jupiter's clouds, something that connects the visible atmosphere to the magnetic core, a boundary, a transition, a threshold. And above that line, the atmosphere moves freely, carries chemistry, generates storms, and steers the magnetic field. Below it, the electrical conductivity increases sharply, and the fluid dynamics change. These two worlds, the outer atmosphere and the conducting interior, are not isolated from each other. They are dynamically coupled. But they are also, in a meaningful sense, distinct. This distinction has profound implications for the deepest mystery of all. Stand at Jupiter's North Pole, if you could, and look up.
What would you see with human eyes? Nothing unusual. The aurora glows in wavelengths our eyes cannot detect. But if you could perceive ultraviolet light, you would see something that makes Earth's northern lights look like a birthday candle compared to a bonfire. Jupiter's auroras are the most powerful in the solar system, hundreds of times more energetic than Earth's most spectacular displays. And unlike the auroras on Earth, which flare during periods of high solar activity and then fade, Jupiter's auroras never stop. They are permanent, continuous, eternal. The source of this perpetual light show is the conjunction of Jupiter's immense magnetic field and its extraordinary family of moons. Jupiter's innermost large moon, Io, is the most volcanically active body in the solar system. Its surface is constantly being reshaped by hundreds of erupting volcanoes, driven by the tidal flexing that results from Io being squeezed and stretched by Jupiter's gravity as it orbits Jupiter. These volcanoes pump roughly a ton of material into space every second: sulfur dioxide, sulfur, oxygen, and other compounds that are rapidly ionized by Jupiter's intense radiation environment. This material becomes trapped in Jupiter's magnetosphere, forming a torus of plasma that encircles the planet. As Jupiter rotates, completing a full rotation in less than 10 hours, remember, it drags this magnetosphere with it, flinging ions toward the poles and generating powerful electrical currents. The energy dissipated in Jupiter's upper atmosphere by these currents is staggering. When high-energy particles rain into Jupiter's upper atmosphere and collide with hydrogen molecules, those molecules are excited to higher energy states. When they relax back down, they release photons, light, primarily in the ultraviolet and infrared portions of the spectrum. The result are those immense oval rings of auroral light encircling the poles, each aurora roughly the size of Earth. But here's where the detail becomes extraordinary, because Jupiter's auroras contain footprints. As Io orbits Jupiter, it carves a path through the plasma torus, generating a magnetic flux tube, essentially a tube of intense electromagnetic activity connecting Io to Jupiter's polar atmosphere. Where that flux tube meets the atmosphere, there is a bright auroral spot, a footprint, an Io-shaped signature in Jupiter's northern and southern lights, moving along the auroral oval as Io moves in its orbit. Europa has one too. Ganymede has one. These moons, hundreds of thousands of miles away, are each leaving their marks on Jupiter's polar atmosphere like pen nubs dragging across paper. Meanwhile, Hubble telescope observations have revealed auroral curtains rising thousands of miles above the cloud tops, structures that dwarf anything ever seen on Earth. And researchers using the Chandra X-ray Observatory have detected something even exotic: X-ray emissions from Jupiter's poles. Jupiter's aurora doesn't just glow in ultraviolet, it produces X-rays. The physics of how particles are accelerated to energies sufficient to generate X-ray aurora is still being actively researched. Jupiter's poles are not quiet places. They are the endpoints of some of the most energetic electromagnetic processes in the entire solar system.
We think of rings when we think of Saturn. Saturn's rings are legendary, brilliant, vast, made of billions of ice chunks ranging from dust particles to boulders as large as houses, reflecting sunlight so powerfully that they can be seen with a good pair of binoculars from Earth. Jupiter has rings too. You would be forgiven for not knowing this. They are among the faintest objects in the solar system, 1,000,000 times fainter than Jupiter itself. They were discovered only in 1979, when the Voyager 1 spacecraft captured a backlit exposure that revealed their ghostly presence. They were not seen in reflected sunlight from ahead. They had to be photographed against the light source, the way you see a fine dust cloud when sunlight streams through a window at the right angle. The James Webb Space Telescope has since given us the sharpest views of Jupiter's ring system yet, and while they remain thin, tenuous, and structurally simple compared to Saturn's grand architecture, they have their own story to tell. Jupiter's ring system consists of a main ring, a narrow, relatively bright band encircling the planet at the equator, surrounded by an inner halo ring that extends slightly inward, and two wide, diffuse outer rings called the Gossamer rings, which span a much larger region.
The system is composed not of ice, but of tiny particles of dark silicate rock, essentially microscopic specks of debris. Where does the material come from? From the planet's own small inner moons. When tiny meteoroids, specks of space debris moving at high velocity, strike the surfaces of Jupiter's small inner moons, the impact blasts material off the surface. Unlike a large moon like Ganymede or Io, which has enough gravity to hold ejecta back, these tiny moons, Adrastea, only about 12 miles across, Metis, slightly larger, can barely hold on. The impact debris escapes into orbit around Jupiter, and over millions of years, countless such impacts have built up a continuous supply of ring particles. Adrastea orbits right at the outer edge of the main ring and is its primary material source. The gossamer rings are fed by two slightly larger moons, Amalthea at about 155 miles across, and Thebe, whose dust forms the wispy outer extensions of the system. The rings are so thin, the main ring's vertical thickness is just a few miles, and so dark that they absorb almost all the light that hits them. They are best observed not in reflected sunlight, but in transmitted light, with the ring illuminated from behind. This is why they were invisible to ground-based observers for so long, and why spacecraft images taken looking back toward the sun reveal them so dramatically. Saturn's rings may be more spectacular, but Jupiter's are more fragile, more fleeting, and in some ways more poignant. Not the grand remnants of a shattered moon, but the quiet, ongoing accumulation of 1 million microscopic impacts, each one kicking a tiny puff of rock dust into eternal orbit.
Everything we have described so far, the storms, the jets, the lightning, the auroras, the rings, exists in the outer shell of Jupiter, the part we can touch directly or indirectly with our instruments. But Jupiter is not just its atmosphere. Most of its mass lies in the interior, and it is in the interior where the deepest mysteries reside. For decades, the standard model of Jupiter's interior was relatively clean, an outer layer of molecular hydrogen and helium, the atmosphere and the layers beneath it. Below that, at depths where pressure reaches millions of atmospheres, the transition to metallic hydrogen, and at the very center, a compact, rocky or icy core, perhaps 10 times the mass of Earth, containing the heavy elements, oxygen, carbon, silicon, iron, that accreted during Jupiter's formation from the early solar system. This model was elegant. It was consistent with the gravitational measurements available at the time, and it was almost certainly wrong. The Juno spacecraft, which entered Jupiter orbit in 2016, has transformed our picture of the interior, not by directly seeing inside the planet, no instrument can do that, but by measuring Jupiter's gravitational field with extraordinary precision. Here's how it works. As Juno sweeps close to Jupiter on each orbit, Jupiter's gravity tugs on the spacecraft. By tracking Juno's velocity with extreme precision, using the Doppler shift of the radio signals it sends back to Earth, scientists can measure tiny variations in the gravitational field from one region to another. These variations encode information about how mass is distributed within the planet. When researchers attempted to construct interior models that matched the gravitational data Juno collected, they found something they had not expected. A relatively small, compact core, the old model's neat package of heavy elements at the center, could not reproduce the measurements, but another type of structure could. A dilute core, a fuzzy core, an extended interior region, potentially reaching as far as 30% or even more of the planet's total radius, where heavy elements are not confined to a compact central object, but spread out, diluted with hydrogen and helium in a gradual compositional gradient extending far from the center. In this model, Jupiter doesn't have a core in the way Earth has a core. It has a smeared-out reservoir of heavy material that blends gradually into the surrounding hydrogen envelope with no sharp boundary between core and mantle.
Heavy elements dissolved into the depths of a fluid planet, spread through a region thousands of miles across. The term planetary scientists use is an extended diffuse core, or a fuzzy core, and it has implications that cascade through everything else we know about Jupiter. If Jupiter's heavy elements are distributed this way, then the composition of the planet's observable atmosphere, the part we can actually sample, may not reflect the composition of the interior at all. There could be vast reservoirs of water, oxygen, and other compounds locked deep inside the planet, beneath the 2,000-mile boundary where atmospheric dynamics give way to the electrically conducting interior, and where none of our atmospheric chemistry measurements can reach. Which brings us to what may be the most consequential and most confusing recent discovery about Jupiter: the water problem.
In the early solar system, there was a boundary. Scientists call it the snow line, the distance from the young sun beyond which temperatures were cold enough for water ice to condense and remain solid. Inside the snow line, the inner planets formed in a drier environment. Outside it, where Jupiter formed, water ice was abundant. It was one of the building blocks of the planet. The implication is clear. Jupiter should contain a lot of water, significantly more water relative to its total mass than the Sun itself. When planetary scientists calculate how much Jupiter should have accumulated during its formation, given its location beyond the snow line, and given the standard models of how giant planets collect material, they arrive at an oxygen to hydrogen ratio significantly higher than solar. Jupiter should be substantially enriched in oxygen, and most of that oxygen should be bound up in water molecules. Detecting that water has proven surprisingly difficult. The Galileo probe, the only spacecraft ever to descend directly into Jupiter's atmosphere, entered in 1995 and fell for 57 minutes before being crushed by the pressure. It measured less water than expected, but it had the misfortune of entering in a dry, anomalous region called a hotspot, a meteorological feature analogous to a dry, clear eye within a storm system, and its measurements were probably not representative of the global average. Juno's microwave radiometer, designed to peer much deeper into the atmosphere than any previous instrument, offered a second attempt. Its measurements suggested a more reasonable water abundance near the equator, about twice the solar value. But the picture is complicated by the fact that water is unevenly distributed with latitude and depth. And then, in 2026, a new study led by Yahun Yang used a different approach entirely. Instead of measuring water directly, the team modeled the distribution of carbon monoxide in Jupiter's atmosphere using chemical kinetics, tracking the reactions between molecules, combined with large-scale models of atmospheric circulation. Why carbon monoxide? Because in the deep, hot layers of Jupiter's atmosphere, water and methane react to produce carbon monoxide. The carbon monoxide then gets carried upward by atmospheric mixing into the observable upper atmosphere. By measuring the carbon monoxide abundance, which is much easier to observe than water directly, and working backward through the chemistry, you can constrain the amount of water present in the deep layers where direct measurement is impossible. The result was startling. The chemical data pointed to an oxygen enrichment of only about 1 to 1.5 times the solar value, barely above solar. For a planet that formed beyond the snow line where water ice was supposed to be plentiful, this is unexpectedly low. But here's where the interpretation splits, because the model that links carbon monoxide to deep layer oxygen depends on an assumption that Jupiter's atmosphere is reasonably well mixed from top to bottom, that material circulates freely between the deep layers and the upper atmosphere. And as we have already seen, the evidence from Juno's gravity measurements strongly suggests that this assumption is wrong. Jupiter's interior may have sharp compositional gradients, barriers to mixing. The 2,000-mile boundary between the outer dynamic atmosphere and the conducting interior may act as a lid, preventing material from below from freely circulating upward.
If that's true, then the low oxygen signal in the carbon monoxide measurements may not mean Jupiter lacks water. It may simply mean that most of Jupiter's water is locked beneath the mixing boundary, inaccessible to the atmosphere above, invisible to our chemistry instruments. The water isn't absent, it may just be hiding. And making this even more complex is a further refinement of the picture delivered in 2026 from a completely different source: the shape of the planet itself.
Measuring the precise shape of a giant planet from millions of miles away sounds like a task of staggering difficulty. And it is, but the physics provides a path. Jupiter is not a perfect sphere. It is an oblate spheroid, flattened at the poles and bulging at the equator, distorted by the centrifugal force of its rapid rotation. The exact degree of that flattening depends on how mass is distributed within the planet. A planet with more mass concentrated at its center would be less oblate than one with mass distributed more evenly toward the equator. Jupiter's precise shape is therefore a window into its internal structure. In 2026, researchers used radio signals from the Juno spacecraft to refine Jupiter's shape measurement with unprecedented accuracy. As Juno's radio transmissions passed through Jupiter's atmosphere at different angles during various orbital configurations, the signals were slightly refracted, bent, and delayed by the atmospheric gas. By analyzing the precise pattern of these delays and frequency shifts, scientists could reconstruct the structure of the atmosphere and determine the planet's curvature with extraordinary precision. The result was a small but significant adjustment to the known shape of Jupiter. The planet is approximately 5 miles narrower at the equator and about 15 miles more flattened at the poles than previously measured. 5 miles on a planet 86,000 miles wide. That sounds trivial, and in everyday terms it is, but in the context of interior structure modeling, it is not trivial at all. Every model of Jupiter's interior must simultaneously reproduce the planet's gravitational field, the behavior of its magnetic field, the depth of its atmospheric winds, and the shape of the planet itself. These are not independent constraints. They all depend on the same underlying interior structure. When one of them shifts, even slightly, the entire model must be adjusted. The revised shape tightens the constraints on Jupiter's interior, ruling out some configurations and making others more plausible. Combined with the fuzzy core hypothesis from the gravity data, the magnetic depth constraints from Juno's magnetometer, and the revised chemical abundances from the carbon monoxide analysis, the new shape measurement sharpens the outline of a Jupiter whose interior is layered, stratified, and deeply complicated. Each instrument, each approach, each measurement illuminates a different depth. None of them alone can tell the whole story. Atmospheric chemistry probes the region above the mixing boundary. Gravity measurements reveal the distribution of mass in the deep interior. Magnetic field mapping constrains the dynamics at 2,000 miles depth and below. Shape measurements constrain the integrated distribution of mass from top to bottom. Storm depth measurements tell us where the dynamic weather layer ends. Together, they are beginning to converge on something. A picture of a planet that is not the uniform, simply structured sphere of the old textbooks, but something far more interesting. A layered world with distinct regions separated by boundaries that regulate the flow of chemistry, heat, and magnetic influence between them. A planet still in the process of becoming what it will eventually be. It is worth pausing in the midst of all this complexity to appreciate what Jupiter fundamentally is. Jupiter is composed almost entirely of hydrogen and helium, the same two elements that make up the Sun, the same elements that were the raw material of the universe in the moments after the Big Bang.
Of all the planets in our solar system, Jupiter is by far the most stellar in its composition. It is, in a meaningful sense, a failed star. Not failed in a derogatory way, but failed in the sense that it simply did not accumulate quite enough mass to sustain hydrogen fusion in its core. The minimum mass required to sustain hydrogen fusion to become a true star is about 80 times the mass of Jupiter. Jupiter is 1 Jupiter mass. It came nowhere close. But it is not as far from starhood as it might seem. There are objects called brown dwarfs, objects too massive to be planets, too small to fuse hydrogen, that occupy the space between 13 and 80 Jupiter masses. The smallest confirmed red dwarf stars are only about 80 times more massive than Jupiter. In the grand taxonomy of astronomical objects, Jupiter is on the low end of a continuum that runs from giant planets to brown dwarfs to stars. Jupiter does, in fact, radiate more energy than it receives from the Sun. This is not because it is fusing hydrogen, it is not, but it is still slowly contracting under gravity, and the gravitational energy released by that slow contraction emerges as heat. This process, called Kelvin-Helmholtz contraction, is what powers brown dwarfs. Jupiter, in its cold and quiet way, is still doing the same thing, slowly, imperceptibly, releasing the stored-up energy of its violent formation 4.5 billion years ago. This makes Jupiter not merely a planet, but a window into stellar physics, a laboratory for understanding the processes that govern objects at the boundary between planets and stars, right here in our own cosmic backyard.
None of what we have discovered about Jupiter in the past decade would have been possible without the Juno mission, and it deserves a moment of recognition. Launched in 2011, Juno arrived at Jupiter in July 2016 after a 5-year journey that took it once around the Sun and back to use Earth's gravity for a speed boost. Its orbit is a highly elongated ellipse. It sweeps in close to the cloud tops once every orbit, then arcs far out into the outer solar system, spending most of its time far from Jupiter to minimize its exposure to the planet's lethal radiation belts, which could quickly destroy electronics not designed for that environment. Juno carries 9 scientific instruments: a microwave radiometer to probe the atmosphere's deep layers, a gravity experiment based on precise radio tracking, a magnetometer, an ultraviolet imaging spectrograph to study auroras, a Jovian infrared auroral mapper, a plasma and particle detector, an X-ray detector, and a visible light camera called JunoCam, which has produced many of the extraordinary close-up images of Jupiter's clouds that the public has come to know. What Juno has achieved is a wholesale revision of Jupiter science. The discovery of the deep jets, the mapping of the irregular magnetic field and the Great Blue Spot, the confirmation of shallow lightning and mushball hailstones, the polar cyclone geometries, the constraints on the fuzzy core, the secular magnetic variation. Each of these findings would by itself constitute a landmark discovery. Together, they represent a revolution. And the mission continues. Extended through at least 2025, Juno has made close flybys of several of Jupiter's moons, including Ganymede, Europa, and Io, providing the first close-up views of these worlds in decades. Its observations of Io's volcanic activity have been spectacular, capturing erupting volcanoes in real time during multiple close passes. The data from Juno will continue to be analyzed for years after the mission ends. Many of the results discussed in this film are based on data collected during the extended mission phase, and still more discoveries are likely waiting in the archived observations. Let us go inside Jupiter one last time. Not with instruments, not with spacecraft, but with imagination guided by science. The cloud tops are where the story begins. The visible face, the canvas of storms and jet streams we have been exploring. Below the clouds, the pressure increases rapidly. The atmosphere deepens into a thick layer of molecular hydrogen, hydrogen in its ordinary, non-conducting state, stretching thousands of miles deep. The temperature and pressure both climb with depth, and the distinction between gas and liquid begins to blur. There is no sharp boundary where Jupiter's atmosphere becomes its interior. The gas simply becomes denser and denser, transitioning continuously into a supercritical fluid. At roughly 2,000 miles depth, the critical boundary we have encountered throughout this journey, hydrogen begins to conduct electricity. This is not yet the fully metallic hydrogen of the deeper interior, but a transitional zone where the increasing conductivity begins to couple atmospheric dynamics to magnetic forces. The jet streams reach this depth and effectively end here. Below this point, the nature of the fluid motion changes. Deeper still, at pressures exceeding 1,000,000 times Earth's atmospheric pressure, hydrogen becomes fully metallic. The electrons are no longer bound to individual nuclei. They're free to roam through the entire fluid, and the hydrogen has become an extraordinarily good electrical conductor. This is the dynamo region, extending from roughly 0.81 of the planet's radius inward toward the center. Convection in this metallic layer, driven by Jupiter's residual heat, generates the magnetic field. The great blue spot and the secular variation we see at the magnetic surface are expressions of fluid motions here.
And at the center? Here, the honest answer is, we do not know. Not precisely. The old model placed a compact solid or liquid core of heavy elements, rock, ice, iron, containing about 10% of Jupiter's mass, perhaps the size of Earth or a few times larger. The new model, emerging from Juno's gravity data, suggests instead a dilute, fuzzy core, an extended region perhaps reaching 30% of the planet's radius, where heavy elements are dispersed through the hydrogen rather than concentrated in a central object. How did such a structure form? One possibility is that Jupiter was, in fact, born with a compact core, as the old models predicted, but that over billions of years, convective mixing has gradually eroded the core boundary, dissolving heavy elements into the surrounding metallic hydrogen and creating the smeared-out gradient we observe today. Computer simulations suggest this is possible on timescales of billions of years. Another possibility is that Jupiter never had a simple compact core to begin with, that the early processes of giant planet formation deposited heavy material in a more distributed way from the beginning. Or, and this is the frontier, the answer may be something that neither model yet accommodates. The constraints from gravity, magnetism, atmospheric chemistry, and planetary shape all point toward a complex interior. But they do not yet point to a single coherent picture. Every proposed model of Jupiter's interior still has tensions with at least some of the observational data. Jupiter's interior remains, in the most literal scientific sense, an open question. And open questions are the most exciting things in science. We began by listening to Jupiter, and what we have heard, after decades of observation, after missions stretching from Voyager to Galileo to Juno, after analysis that has consumed the careers of hundreds of scientists, is not a simple story. It is not a story of a well-understood gas giant, catalogued and filed away. It is a story of a world that keeps surprising us, a world that hides its water in mysterious depths, that sustains storms for centuries with no intention of stopping, that organizes its polar vortices into geometric patterns that challenge our atmospheric models, that generates magnetic variations through motions we are only beginning to trace, that may contain a core unlike anything we expected to find. The more precisely we measure Jupiter, the more questions we uncover. The more data Juno returns, the sharper the outlines of our ignorance become defined. This is not a failure of science, it is its greatest triumph. Every question answered by Juno has revealed two more beneath it, and those new questions are better, deeper, more interesting than the ones they replaced.
Jupiter is 483 million miles from Earth at its closest. It has been there for 4.5 billion years. It will be there for billions more. And for all that time, it has been doing what it does, spinning, storming, radiating, humming with electromagnetic energy, slowly releasing the memory of its violent formation into the darkness. We have been watching it for 4 centuries. We have been visiting it for 50 years. We have been mapping its interior for a decade. And we are still, in the most profound and humbling sense, at the beginning.